Now it should stand to reason that if the derivative of e to the x is e to the x, then the integral of e to the x dx should also be e to the x plus c. And that's true. The other thing that should follow based on previous work is that if the exponent is something other than just x, then we are going to end up with e to the u in the problem, but we're going to have to pay attention to using the chain rule. So let's look at some examples involving integration. We've got the integral of e to the 5x dx. Now some of you can see how this will be related to unpacking the chain rule and can recognize this must be 1/5 e to the 5x plus c. And if you couldn't see this, then we could use u substitution and say that u equals 5x, so du equals 5 dx, or 1/5 du equals dx, which means that our integral by u substitution will become 1/5 times the integral of e to the u du. But the integral of e to the u is itself, so we'd have 1/5 e to the u plus c, but we set u equal to 5x, so we've got 1/5 e to the 5x plus c. Again, using u substitution to help you stay organized is a great strategy, and there's nothing wrong with it. If you can see the chain rule sometimes, and that's a good thing as well. Let's consider the integral of 4 times e to the 1 minus x dx. Well, I know that when I integrate, I should get the function itself, but by the chain rule, there should be a -1 involved with my leading coefficient, so this must have been -4 originally, plus c. And one thing you can do to test this is just take the derivative of your answer. You should get back to where you started. Let's consider a different problem. Perhaps the integral of 2x e to the x squared dx. Now I can already see how the chain rule is going to be involved with this, and can recognize this is going to have to be e to the x squared plus c. If you can't see that, if we use u substitution, u equals x squared. So du equals 2x dx. So by u substitution, we're integrating e to the u du, which is just e to the u plus c, but u had the value of x squared. So that's why our answer is e to the x squared plus c. Another example, integrating, this would be the integral of e to the 1 over x, or x to the -1, I'll write it like they did, over 2x squared dx. Well, I'm not really sure how to approach this, so I'm just going to start saying that u equals 1 over x, which means that u is x to the -1. Then du will equal -x to the -2, or -1 over x squared. Now, I need this to be 1/2 of times x squared rather than -1 over x squared. So what I'm going to do is multiply both sides by -1/2 in order to get the piece that I want. There should be a dx here. That will cause this to become 1 over 2x squared dx. I just multiplied both sides by 1/2. Now I've got all the pieces I need in order to make my substitution. This integral will end up being e to the u du times -1/2. Integrating, I'm going to get -1/2 e to the u plus c, but u had the value of 1 over x, so I have -1/2 e to the 1 over x plus c. Right, so I just used some basic algebra to help me out. Let's consider the integral of cosine x times e to the sine x dx. I know that this must have come from e to the sine x plus c, because by the chain rule the derivative of sine x is cosine x. What about the integral of e to the x over 4 minus e to the x dx? Well, if I let u equal 4 minus e to the x, then du equals negative e to the x dx, or negative du equals e to the x dx. So this is negative 1 times the integral of 1 over u du. The integral of 1 over u is the natural log of the absolute value of u plus c, but we said that u had the value of 4 minus e to the x plus c, and we could stop there. Alright, what about the integral of e to the x minus e to the negative x over e to the x plus e to the negative x dx? Now in previous work we've seen the relationships between these two things. So if u equals my denominator in this case, and if I wasn't sure, if I didn't have previous work, I would just choose a value for u and see if the substitution will work or not. Then du would equal e to the x minus e to the negative x dx. So I can make my substitution. This is equal to the integral of 1 over u du, which is equal to the natural log of the absolute value of u plus c, which is equal to the natural log of the absolute value of e to the x plus e to the negative x. And a common mistake here would be to get confused about some some natural log properties and try and simplify this, and you can't really simplify this given any properties that I'm aware of offhand. There may be one, but we've never studied it. Let's consider the integral, finally, of e to the 4x plus 2e to the x plus 1 over e to the x dx. Again, I'm not going to lose sight of all the things that I've studied up to this point. This is equal to the integral of e to the 3x plus 2 plus 1 over e to the x dx. And so when I integrate this, I'll have 1/3 e to the 3x plus 2x minus e to the negative x plus c. Here we have a variety of examples of integrating involving e to dx. Apparently there's going to be a part 4 of this, and we'll be looking at some more ideas involving area, some ideas involving volume, and some other aspects involving e and natural log.